Welcome to MOVITRAC LTP-B Basic and Intermediate Training. This is session 12. We're almost done with our class. This is the second to the last session. We have just one more after this. In our last session, we learned a lot about field buses and the MOVITRAC LTP-B's communications capability. We're going to continue with that today. We're going to move on to actually using the field bus to control our VFD. So the topic of today is field bus control. If you're a PLC programmer, this session should be a great help to you, so pay attention. I'm sure you'll find it interesting. So we're going to talk about field bus control, what you have to do on the software side of things to make your MOVITRAC LTP-B operate. Now I'm going to give you a very important note here that will kind of clarify the direction that we're going. Each field bus standard that you use with the MOVITRAC LTP-B, for example, S-Bus, CAN-Open, Modbus RTU, or one of the Ethernet-based field bus standards like Ethernet IP, Modbus TCP, Profinet, or EtherCAT, each one of those standards is different. But what you do to control the VFD is exactly the same. What you send over the field bus to the VFD, commanding it to operate, telling it what speed to turn, these things are the same. They're independent of the field bus. So we're going to focus on that side of things. What you actually send to the VFD, what you interpret coming back from it. I'm also going to mention something else. What you must do to program your PLC depends on the PLC brand. If you're using an Allen Bradley PLC made by Rockwell, then its programming system is different from the system used by, say, a Siemens PLC. And of course, there are 5 different PLC programming languages that you can use. Now, we're not going to get stuck in the weeds with that because it would make this session absurdly long. We would have to cover all the major brands. We'd have to cover at least one programming language. We're not going to do that in this session. What we're going to focus on instead is what you need to send to the VFD or interpret coming back from it. This will be the same regardless of the programming system you use. So you're going to have the understanding of your particular programming system, but we will tell you the protocol that you need to send to the VFD, and we'll go over the protocol of what comes back. So hopefully that will make it clear. If not, just keep watching, and I think everything will be clear by the end. I'm also going to introduce you to a free diagnostic and testing tool that SEW Eurodrive makes available, and you can use it to play with your VFD over a field bus. You don't even have to get into PLC programming just to do that, and I'll be demonstrating that at the end. So on that rather weighty note, let's get going. Let's talk about how field bus control works. What is it that you do when you want to control your VFD over a field bus? Well, let's just set up a generic field bus here. We have a PLC, in this case a Siemens. We have 3 MOVITRAC LTP-Bs, and they're connected up to the field bus. It doesn't really matter which field bus we're talking about. What does the PLC have to do to control these VFDs? Devices on a field bus communicate by exchanging what are called process data words, or PDs. Process data words are very, very important. We're going to spend this entire session learning about process data words because that is what your program running in the PLC has to create and then launch onto the field bus to control the VFDs. And the VFDs will send process data words back. It's up to your PLC program to take those process data words and interpret what they mean. Now, the first thing you need to understand is that there are 2 kinds of process data words, what are called process output words, or POs, and process input words, or PIs. This labeling is from the perspective of the PLC. So in other words, process output words go from the PLC to the VFDs. The PLC outputs them onto the field bus. Process input words go to the PLC from the VFDs. So in other words, the PLC inputs them from the field bus. Here's how this works. I'll animate this here. Let's say we're trying to control our 3rd VFD on the field bus. We set our program up, we create the process data words, we address the 3rd VFD, and what happens is a group of process output words, POs, in this case 3 of them, go to the VFD, and they make something happen. and then it sends 3 process input words, PIs, back to the PLC, reporting its status, telling what's going on. That is field bus control in a nutshell. The PLC launches POs to different VFDs telling them what to do. The VFDs send PIs back reporting what's going on. That's it. Now, we're going to talk about something called 3PD control. What is 3PD control? Well, multiple SCW Eurodrive products use a system called 3PD when they are communicating on a field bus. This is a semi-standard form of control that our products use, or at least many of them do. Once you've learned this, you'll be able to work with a variety of products. So that's what we're going to focus on. I think you can guess why it's called 3PD, because the PLC and the VFD exchange 3 process data words in each direction, 3 POs and 3 PIs. So let's again set up our hypothetical field bus with a PLC and a VFD on it. The PLC transmits 3 process output words to the VFD. The first one is what's called the control word. It tells the VFD what to do, whether to run or stop. The second process output word is the speed at which the motor is to turn. And the third process output word is the ramp, which tells it the acceleration and deceleration times. And that's it. It's actually a very simple form of control. Now, the VFD is going to send 3 process input words back to the PLC to give it information as to what's going on. Process input word 1 is a status word. It indicates if the VFD is running or if it's halted, if it's in a fault condition. Process input word 2 is the current speed at which it's turning. And process input word 3 is the amount of current that the VFD is delivering to the motor. And that is it. 3PD control is pretty simple. So that's what we're going to learn. And if you're a PLC programmer, you will have to create these process output words and interpret these process input words. And that is the purpose of this session, to explain to you how to do that. Now, some very important notes here. Listen closely. Depending on the field bus type, whether you're using classic field bus, an expansion card, or the field bus gateway, the MOVITRAC LTP-B can actually support either 3PD or 4PD control. 4PD control uses 4 process data words in each direction instead of 3. It depends on the type you're using. Now, to keep things manageable, we are going to concentrate on 3PD. But do be aware that process output words 2 through 4 and process input words 2 through 4 are totally customizable. What they do is customizable. You set it up in LT shell through the parameters in group 5. Now, what I'm going to do, just to keep things simple and consistent, and so we don't have to explain every imaginable possibility, is we're going to configure the VFD to operate in the standard 3PD mode common to many SCW Eurodrive products. I say standard in quotation marks because 3PD mode actually does vary a little bit with some SCW Eurodrive products. It's basically the same, but there are minor differences. So I'm going to set it up in a way that is relatively consistent with that standard. All right, well, with that out of the way, let's move on. How do we set up our VFD to operate in standard 3PD control? Well, of course, we go into LT shell and we set a few parameters. They're all in parameter group 5, so here's what we need to do. First of all, we set parameter 5-09 to 1, which is speed as a percentage. This is actually the default, so if you haven't changed it, it will already be at this value. It means that process output word 2 is going to contain the speed expressed as a percentage. Then you set parameter 5-07 to enable and parameter 5-10 to ramp time. What this will do is it will make process output word 3 contain the ramp value. We have to set it, and we also have to enable that feature so the VFD doesn't use its parameters for the ramps. Instead, it looks to the field bus. Process output word 4 we're not going to use because this is 3PD, so we turn it off. We set it to no function, which is option 7. Process output word 1 can't be changed. It's always the control word. That's why we don't have to set it, and it doesn't appear here. And that takes care of the process output words. Now we have to set up the process input words. Process input word 1 is always the status word, so that's why it doesn't appear here. You can't change it. But we set parameter 5-12, process input word 2, to speed as a percentage. That's the default. Parameter 5-13, which is process input word 3, is current. We set that to 2. It's already the default, actually. Current is a percentage. And we can't turn off process input word 4, parameter 5-14. It just defaults to power, so we're going to ignore it. So it really doesn't matter what you set it to. We're not even going to be working with it. And yes, if you notice that, there is a typo in LT shell. Parameter 5-14 should be process input word 4, not 3. All right, a few notes here before we move on. When you do regular speed changes in 3PD mode, the ramp will come from process output word 3. It will not use the parameters in the VFD. It will use whatever value you send over the field bus. So regular speed changes, either accelerations or decelerations, will use PO3. The normal stop will also use whatever ramp you have in PO3. So if you say do a normal stop, it will not go to the usual parameter that we've been seeing a lot. It's going to go to process output word 3, and it will decelerate using that ramp. However, if you request a rapid stop over the field bus, it will use a parameter. It will use the familiar parameter 2-25, so do be aware of that. You need to have that set correctly if you want your rapid stop to do what you expect. And you can also do what's called a controller inhibit type stop over the field bus. If you do this, the VFD will go into coast to stop mode. If you have a brake, of course, then it will apply and stop it quickly. But if you don't have a brake, then your VFD will coast. And if you've got a big load attached to it, it may take a while to stop. So be aware of all these things. Nothing really different here, but I wanted to clarify how it works. All right, so let's talk about process data words in more detail. If you're a PLC programmer, this may be familiar to you, but if you're not, pay attention, listen closely, replay things if necessary. We'll get into how the process data words are constructed and how we interpret them. So, process data words. They are 16-bit binary numbers, like this. They have 16 bits numbered 0 through 15. The bit on the right side is the least significant bit, the one of lowest value, and the one on the left is the most significant bit, the one of greatest value. Binary numbers that are acting as process data words perform two types of functions. The individual bits might have significance. In other words, the individual ones and zeros turn things on or off, sort of like switches, or they reflect status information depending on whether they're on or off. So when you're working with a process data word of this type, you're looking at the individual on and off scattered throughout the word. Now, the second type of process data word, the bits form a single number. In other words, all those binary bits together represent a value. We call these parameter words. They could, for example, indicate the speed at which the VFD is to rotate, the amount of current that it's drawing, things like that. So we're going to see both of these types because you use both of them when you're controlling a VFD with process data words. Now, an important concept here. Control systems usually work with binary or hexadecimal numbers rather than decimal. Decimal, as you know, is the kind of numbers that we learned in kindergarten, numbers based on units of 10 and fractions based on units of 10 as well. Control systems really don't work too well with decimal numbers. Binary works really well. We turn things on and off with it. We're interested in individual bits. Hexadecimal numbers, however, can be very convenient too in a control system, and the reason is you can convert binary numbers back and forth between hexadecimal very easily. Hexadecimal, which is called base 16, uses units of 16 rather than 10 like we do in decimal. It has the digits 0 through 9, just like we do in decimal, but it also has 6 additional digits, and they are the letters A, B, C, D, E, and F. So hexadecimal numbers are easy to spot because you see numbers 0 through 9 plus those 6 letters in them as well. Now, if you're creating a control process output word, you usually create it by writing it down as a binary number first, since you're using the individual bits to control functions, and then you convert it to hexadecimal before you send it over the field bus. Parameter POs are usually created as decimal numbers. For example, if you're sending the VFD the speed you want it to turn, you will usually create that as a decimal number, and then you convert it to hexadecimal. Now, maybe at this point you're starting to panic and you're saying, whoa, I don't really understand binary and hexadecimal very well. Should I bail out of this and just end the class right now? No, hang in there. I'm going to show you an easy way to work with binary, hexadecimal, and decimal values. And that is using a tool that you have right in front of you, your Windows calculator. If you fire up the Windows calculator and change it to programmer mode by clicking the little control box in the upper left corner, it will automatically handle these numbers for you. And I'm going to show you how to use it. So if we want to take a binary number and convert it to hexadecimal, here's what you do. First of all, you click here until it changes to Word. That will limit your results to 16 bits, which is the size of a processed data word. So change the calculator to Word mode. Then click Bin to put it in binary mode, and then enter the binary number. Enter the zeros and ones, and the hexadecimal value will be right here. So if I put in 0100, 0110, that turns into hexadecimal 46. Now, since we want to work with 16-bit values, if the hexadecimal value has fewer than 4 digits, just add some zeros to the left side. So the number should actually be 0046. That is a 16-bit hexadecimal number. Pretty simple. Now, what if you want to convert a decimal value to hexadecimal? What do? Almost the same thing. You make sure you're in Word mode by clicking here until it changes to Word. Then you click decimal right here to put it in decimal mode. You then enter your decimal number, and if you want to make it a negative number, click the plus minus key, and then the hexadecimal value will be right there. So in this case, the decimal value, negative 16,384, converts to C000 in hexadecimal. And I'll just mention again, if the value that it converts has fewer than 4 digits, add zeros to the left side. In this case, however, you don't have to. It's already got 4. Little handy tip here. You probably noticed that I had a 0x in front of the hexadecimal numbers. You may wonder, what's that all about? This is something programmers often do. They will often preface a binary or hexadecimal number with the prefixes 0b for binary and 0x for hexadecimal. This just indicates that they're non-decimal numbers. So if you see a number with nothing in front of it, you assume it's decimal. If you see 0b, it's binary. And if it's 0x, it's hexadecimal. That's just programmer convention. But do remember, the preface isn't part of the number. It's just a key for the programmer to keep things straight. All right, with that under control, we're now going to talk about the 3 process output words, PO1, 2, and 3, that your PLC program has to construct and launch onto the field bus to go to the VFD telling it what to do. We're going to start with PO1, which is always the control word. You can't change this to anything else. It's always the same. So remember, this is a 16-bit binary number. In the control word, the individual bits have significance, so they're acting like switches to turn features on or off, so you set or clear those bits as required. Now, interestingly, although there are 16 bits in the word, there are only 4 that have any relevance. They're the ones I've identified in red, bits 0, 1, 2, and 6. All the others are ignored by the VFD. So here's what they do. We'll take a look at the first 3 at the bottom here, bits 0, 1, and 2. Bit 0 is the controller inhibit bit. If you want the VFD to run, you set this bit to 0. So to make this switch operate, you actually turn it to an off condition. It's kind of opposite what you'd expect. And to bring the VFD to a controller inhibit type stop, which is a coast to stop, you set it to a 1. Bit 1 is the enable or rapid stop bit. If you want the VFD to run, you have to set it to a 1. And if you want a rapid stop, you change it to a 0. Bit 2 is the enable normal stop bit. If you want to run the VFD, you set it to a 1. And if you want the VFD to do a normal stop, that is a ramped stop, you change it to a 0. And then this last bit, bit 6, is the fault reset bit. If your VFD is faulted, you can clear the fault over the field bus, What you do is you set this bit to a 1 and then change it back to 0, which is normal operation. Let me show you a number of different patterns here because we're going to use these when we control our VFD. If you want to run the VFD, then you set the bottom bits as follows: 110. Of course, the fault bit is off. So if you convert that binary number to hexadecimal, it is 0006. So if you send a 0006 in P01, your VFD should start turning. If you want to do a normal stop, you send 010 in that word. That translates to hexadecimal 0002. Now, if you look at those bits there, the normal stop bit 2 is 0, so you're requesting a normal stop. Bit 1 is set to run, and bit 0 is also set to run. So that's how you request a normal stop, just by clearing bit 2. If you want a rapid stop, which uses parameter 2-25 for the ramp, you change all the bits to 0, and that will request a rapid stop that gives you hexadecimal 0000. And if you want a control or inhibit stop, then you put 001 in the control word. That's hexadecimal 0001. And then finally, if you want to clear a fault, you set bit 6 to a 1. That's 0040. So you would do that, and then you would change it back to something else later with that bit 0. So that's the control word. Pay attention to these 5 examples because we will be using them in the demonstration that comes at the end of this session. Now, the speed word is probably the most confusing one. This is process output word 2. This is how you tell the VFD how fast to turn. You might think, well, what's so complicated about it? Speed is just an RPM, right? And the answer is no. You're going to express speed instead as a percentage of the VFD's maximum speed. That's the speed value in parameter 1-01. On my demo unit, it's 1800 RPM. Yours, of course, could be different. So we're going to send a percentage. Now, how do we do this? It's a little complicated, so fasten your seatbelt. Here's how we send speeds as a percentage. If we want the VFD to turn clockwise, we send it a positive percentage between 0 and positive 100%. And if we want it to turn counterclockwise, we send a negative percentage between 0 and negative 100%. But instead of sending the numbers 0 to 100, we send the numbers 0 to either positive or negative 16,384. In hexadecimal, that is 4000 or C000. So we need to convert our percentage into the range of 0 to 16,384. You're probably getting a little bewildered right now. You're saying, how do I do this? I'll demonstrate. Just hang on. To convert a clockwise speed, you take the speed that you want to turn and you divide it by the value in parameter 1-01. In my case, I'd use 1800 RPM because that's my maximum speed. So I divide the speed that I want to turn by that value. Then I multiply it by 16,384. I drop any fractions, and then I fire up my Windows calculator and convert it to hexadecimal. To do a counterclockwise speed, I do exactly the same thing, except I multiply by minus 16,384. Otherwise, it's the same procedure. Let me demonstrate with an example. Let's say that I have an 1800 RPM motor on my VFD, so that's the value in parameter 1-01, and I want to turn 360 RPM clockwise. So what I do is I take 360 RPM, divide by 1800 RPM, and that is 0.2. I then multiply 0.2 by 16,384, and I drop any fractions. So I get 3,277. Then I convert it to hexadecimal, which is 0 CCD. So if I send 0 CCD in process output word 2, my VFD should turn at 360 RPM. Yes, that was a lot of steps. Normally your PLC program would take care of this. Let's do a counterclockwise example. Say I have the same motor, 1800 RPM, and I want to turn 900 RPM counterclockwise. I take 900 RPM, I divide it by 1800 RPM, and that is 0.5. I multiply 0.5 by minus 16,384, That gives me negative 8,192. I convert it to hexadecimal with the Windows calculator, and it is E000. So if I send that in PO2, my VFD should turn counterclockwise at 900 RPM, which is 50% of the motor's maximum speed. You might want to review this slide if that didn't make sense, but if it did, let's move on. Our third process output word is the ramp word. This tells the VFD how to accelerate or decelerate when it's changing speeds or when it's doing a normal stop. This one is easy. It's simply sent as a time in milliseconds, 1/1000th of a second. So you take the time you want the ramp to be, multiply it by 1,000 to convert it to milliseconds, and convert it to hexadecimal. Here's an example. Say we want a 3.5 second ramp. We just multiply 3.5 seconds times 1,000 milliseconds per second. That gives us 3,500 milliseconds. We convert it to hexadecimal with the Windows calculator. It is 0 DAC in hexadecimal. Send that in process output word 3, and you should have a 3.5 second ramp. That one was pretty easy. Okay, so that's the process output words. These tell the VFD what to do. So if you send these 3 words over the field bus, your VFD should fire up and do what you expect. Now, the VFD is going to send 3 process input words back to you on the PLC end to tell you what's going on. And here's what they do. Process input word 1 is the status word. It tells you what the VFD is doing. And it looks like this. It's one where the individual bits mean things. So it's going to report its status through individual bits and also an 8-bit number value as well. So this is kind of a hybrid word. It has both a number in it and individual bits. Bit 0 tells you if the VFD is in control or inhibit mode. If there's a 0 in this bit, it is. If there's a 1 in it, it isn't. Bit 1 is the ready signal. If it's a 1, the VFD is ready, and if it's a 0, the VFD is not ready. Bit 2 indicates whether the VFD is listening to process output words. Normally this will be 1, meaning yes, but 2 means no. In other words, it will communicate back to your PLC that it's in some other mode than field bus mode. Bit 5 is the fault bit. If your VFD is faulted, this bit will be 1. If it's normal, it will be 0. In this case, there's no fault. And then the top 8 bits, bits 8 through 15, will either be a fault or status number. So you have to convert these back to a decimal number and then look up that number in the manual. If the fault bit is 0, meaning there's no fault, this will be a status number, just indicating what the VFD is up to. If the VFD is faulted, in other words, bit 5 is 1, this will be a fault code, and your PLC program can interpret that. All right, that's the status word. Pretty straightforward. Process input word 2 will be the actual speed word, so this will change as the motor accelerates and decelerates. If it's running at a steady speed, it should match process output word 2, the speed you've requested, and it's exactly the same as process output word 2 in how it's represented. It's a percentage of the motor's maximum speed, the value in parameter 1-01. So again, same thing. It's going to express this as a number between plus and minus 16,384. And this represents a percentage between 0 and 100%, either clockwise or counterclockwise. So to interpret this, here's what you do. You convert it to a decimal. So take PI2, convert it to decimal, divide by 16,384, and multiply by the speed in parameter 1-01. If it's turning counterclockwise, you do exactly the same thing, but you'll have to convert it to a positive decimal because it will come back negative to begin with. But then you divide by 16,384 and multiply by the parameter 1-01 speed. Here's an example. Let's say you have an 1800 RPM motor on your VFD. Process input word comes back 2F0E. Convert that to decimal. It's 12,046. Take that and divide it by 16,384. It's 0.735. That's 73.5%. Multiply that by 1800 RPM, which is your motor's maximum speed, and you get 1,323 RPM in the clockwise direction. Here's a counterclockwise example. Let's say DE25 comes back You convert it to decimal and it is negative 8,667. That means it's rotating counterclockwise. You drop the minus sign, turn it into a positive decimal number. You take 8,667, divide by 16,384. It's 0.529, which is 52.9%. Multiply it by 1800 RPM, and you get 952 RPM in the counterclockwise direction. So that's what your PLC program would have to do if it wants to monitor the speed coming back from the VFD. Process input word 3 is the amount of current that the motor is drawing. So this is a value, but it is not in amperes, it is in percentage. It's the percentage of the VFD's nominal current value. That's the value in parameter 1-08. So here's how you convert this value to amperes. The value that comes back in hexadecimal will range between 0 and 1000 in decimal, which in hexadecimal is between 0 and 0.3E8. So that's your range. It's in tenths of a percent. So to convert this into current, you convert the hexadecimal number to decimal, divide by 1000, and multiply by the value in parameter 1-08. Here's an example. Let's say my motor is a 1.8 amp motor, so that's in parameter 1-08. PI3 comes back 0.177. I convert it to decimal, which is 375. I take 375 divided by 1000, that's 0.375. That's equal to 37.5%. I multiply that by 1.8 amps, the motor's nominal current, and that's 0.675 amps. So that is the amount of current the motor is drawing at this particular moment. Again, your PLC program would have to do all this math. All right, that was a lot of material to cover. Maybe you want to pause and get a cup of coffee before you continue. We're going to be doing our demonstration in just a minute, but I need to introduce you to the tool we're going to use to demonstrate this. I'm not going to write a PLC program for you. That would take way too long, and this video is already pretty long. I'm going to use a tool that is available for anyone to use. It is free from SEW Eurodrive, and you can use it to play with your field bus without even having to fire up a PLC. It is called the Ethernet Master Simulator. So what are the features of this little tool? It simulates a PLC communicating over a field bus. So what it allows you to do is simply type in the process output words and it will transmit them over the field bus. You can use it for testing and diagnostics to make sure your field bus is working and your VFD is set up correctly. That's how we're going to use it. You can use it either with Ethernet IP or Modbus TCP field buses. You cannot use it with Profinet. It does not simulate Profinet. So it simply sends POs to the device and it monitors the PIs coming back. And that's all it does. It's a very simple tool. You can download it from SEWEurodrive.com. I've included a link in the description below. So I encourage you to download it and install it. So let's just overview it quickly how you set it up. You run it on your PC, and the first thing you do is you enter the IP address of the device you're trying to control on the field bus. In this case, I put in the SEW Eurodrive default address, which is what my demo unit is using right now. Remember, we set it up in our last session. You have to set your protocol to Ethernet IP. If you're using Modbus TCP, of course, you'd pick that, but I'm using Ethernet IP for my demonstration. You set your input and output values to 4. This is saying you want to exchange 4 words in each direction. We're only going to be using 3, but you still have to set it to 4. And then you set RPI to 500 milliseconds. That just ensures it won't time out too quickly. And then finally, you click Open Session, and it will connect to your VFD over the field bus. It should change like this. It will indicate the product name, which in my case is CompactCom Ethernet IP. You need to set a few more things and then you're ready to go. You need to set the assembly instance to 100 and 150. That just tells it how to communicate with this particular card. And then you click Start. And it will change to this screen. You'll see your 4 process output words on the left and your 4 process input words on the right. Before you do anything, however, uncheck Auto Update PO. If you leave this checked, the minute you type a process output word, it will send it onto the field bus that instant, and you might have some unexpected behavior. If you uncheck it, what you will do is you will have to change the process output words, then click Update PO to transmit them. I like that a lot better. So what you do is you edit the POs as required. You set them up in hexadecimal. You click Update PO to transmit them to the field bus, and the process input words update automatically. You'll see these changing as your VFD changes. It's a really simple tool. Not very sophisticated, but extremely useful. Now, an important note about the Ethernet Master Simulator, I want to stress this. SEW Eurodrive offers the Ethernet Master Simulator freely on an as-is basis. They do not guarantee that it will work on your computer. It is not a very polished tool, but we don't sell it. We give it to you for free, so it's as is. If it works for you, great. If you have problems with it, you're kind of on your own. Now, if you have problems getting it to run, here are some tips. You may have a firewall turned on your computer and it's blocking it, or it may be violating your system's IT policy in some way. We cannot help you with that. We're not an IT support department. So if you're having problems, you probably want to contact your IT support department for help. That said, let's move on to a demonstration. Here's what we're going to do. I'm going to use my demo unit as I set it up last time with my Ethernet IP field bus card installed in it. I'm going to control it with the Ethernet Master Simulator. And here's what I'm going to do. I'm going to work out the PO1 values to run, stop, rapid stop, and inhibit the VFD. I'm going to work out the PO2 values to run my VFD at 1500 RPM clockwise and 750 RPM counterclockwise. I'm going to work out the PO3 values for a 5-second and 10-second ramp. Then I'm going to run the VFD and test each speed and ramp. I will test each stop to confirm that it works as expected. I will capture my process input word 1 when the VFD is both stopped and running, and I will interpret what the bits mean. And then I will interpret process input words 2 and 3 when the VFD is running. Finally, I'm going to play with terminal control to show you how it differs from regular terminal control. In field bus mode, it does operate, but in a more limited way. And finally, as a bonus, we're going to test how the VFD handles communications loss during field bus operation. I'm just going to unplug the Ethernet cable and see if the VFD shuts down as we've set it up to do. So that's what I'm going to do. It's a lot of things to demonstrate, so again, keep your seatbelt fastened. First of all, here are all my words worked out. And I want you to be sure that you understand where each of these numbers comes from before continuing to the demonstration. So if any of these don't make sense, you might want to go back, replay this video. Let's just go over them quickly. These are our two speed values, 1500 RPM clockwise and 750 RPM counterclockwise. What I did is I divided these numbers by 1800 RPM, which is my motor's maximum speed. I multiplied it by 16,384 or minus 16,384. I got 13,653 and minus 6,827. I converted those to hexadecimal and I got 3555 and E555. So those are my two speed values. My ramps were easy, 5 seconds and 10 seconds. That's 5,000 milliseconds and 10,000 milliseconds. I converted to hexadecimal and I got 1388 and 2710. So those are my ramps. And then these values I worked out earlier in this session. To get a run, I send 0006 to my VFD. To get a normal stop, 0002. To get a rapid stop, 0000. And a controller inhibit stop, 0001. So these are the values I'm going to be feeding the Ethernet Master Simulator to run my VFD. Let's go and do that. All right, well, before we can actually go in and control our VFD over the field bus, we need to make one little change in here. We need to make sure we're configured in 3PD mode the way I described it in this session. So I'm in LT shell, I've scanned in. I'm going to turn on real-time edit mode and I'm going to go to parameter group 5. I need to do just a few things. I need to check that the POs and the PIs are set up correctly. Now parameter 5-09, PO2 is set to speed. That's fine. Parameter 5-10 should be set to ramp. Now it isn't, so I need to change it to option 3, ramp time. PO4 we're not using, so we'll just leave it set to no function. PI2 is set to speed. PI3 is set to current. We're going to ignore PI4. This is actually PI4, even though it says PI3. Remember, that's a typo in LT shell. That's going to report power, but we're just going to ignore it. We need to do one final thing. We need to tell the VFD to get its ramp value from the field bus rather than using its parameters, which is what it does by default. So we need to go up to parameter 5-07, SBus ramp control, and enable it. And by doing this, it will now listen to the field bus instead of using parameters. The only exception will be rapid stops where it will use parameter 2-25. All right, let's turn real-time edit mode off, and now we're ready to go into the Ethernet master simulator and test things out. All right, well, you can see we have the Ethernet master simulator started up. I'm connected to the field bus card, and I'm ready to go. I've also turned digital input 1 on my VFD, so it's enabled. Just to make things a little easier, I'm going to pop up a little cheat sheet here. This is that table of values that we're going to use as we create our POs. So what we need to do is get connected first of all. Now to do this, I need to change my input and output words to 4 and RPI to 500, and then click Open Session, and you can see it connected to my field bus card. Now I need to change my assembly instances to 100 and 150, and then click Start, which will fire up a session. And you can see we have successfully connected. We're already getting PIs coming back. Now I need to turn Auto Update PO off because I don't want my POs to go out the minute I type them. I want them to wait until I click the Update PO button. So now we're ready to go. We're going to go ahead and try to run our VFD. So I'm going to put in PO 1, 2, and 3. I'll put in a 6 in PO 1. That's going to tell it to run. I need to give it a speed. I'll put in 3555. That's 1500 RPM. And I'm going to use our 5-second ramp, which is 1388. And now I'm going to click Update PO. And we can see our motor has indeed fired up, and it's running. And I'm sure you can hear it as well. You can see my process input words have changed in response. Notice that PI2 is showing pretty much the same value as PO2. This is the speed coming back, and it's pretty close. We also have our current value here at 00B5. I'm going to jot that down. We'll interpret that later. And then, of course, we have our status word here, 05C7. I'll jot that down too so we can look at that later. All right, let's go ahead and change our speed. We're going to go counterclockwise. I'll put in the negative value. E555, I'll click Update PO. And you can see my VFD is decelerating the motor and reversing direction. And it's now running in the opposite direction, so I think that works fine. Now let's go ahead and do a normal stop. This is a ramped stop, so it's going to use the ramp value we supply, and I'm going to switch to our 10-second ramp so we can try that out. I'm going to put in 2710. And then I'm going to request a normal stop by putting in a 2 in process output word 1. And you can see it is decelerating down, and it comes to a stop. And that took about the time we expected. It came down from 750 RPM with a 10-second ramp, which actually only takes 5 seconds for this particular speed. All right, we're going to test our other stops. We're going to re-accelerate, so I need to put in a 6 here. And I'm going to go back to 1500 RPM, so 3555, and I'm going to go to our shorter ramp, 1388. And I'm going to re-accelerate us back up to 1500 RPM. I'm going to call for a rapid stop, which will use parameter 2-25. Remember, we've set it to 1 second. I'm going to put in a 0 in process output word 1. And you can see there we got a very quick stop. It happened in about a second. Let's re-accelerate and let's try a controller inhibit stop. So we re-accelerate back up. I'm going to put a 1 in process output word 1. This will do a coast to stop. And you can see it stopped pretty quickly, so that worked out. All right, so we have tested both speeds, we've tested both ramps, we've tested all our different starts and stops. We've jotted down our PIs when the VFD is running. We just need to jot one more down, and that is this one here when it's stopped, 02C6. So let's go ahead and analyze all this. Okay, well, let's interpret those PIs that we got back when we were running the VFD under field bus control. PI1 when the VFD was stopped gave us 02C6. PI1 when it was running gave us 05C7. PI2 when it was running was 3550, that's the speed PI, and then PI3, which is the current PI, when it was running gave us 00B5. So we're going to have to interpret these in different ways. PI1, of course, is the status word, and we have to look at the individual bits to see what's going on there. So we're going to look at this one first, PI1 when the VFD is stopped, 02C6. You've seen this before. This is the breakdown of the different bits, so we're going to fill it in here with 02C6. We convert this to binary from hexadecimal using the Windows calculator. And we're going to start by looking at the fault bit. That's bit 5. It's 0, which means there's no fault. Therefore, the top 8 bits is a number that represents the status, not the fault condition. If we were in a fault condition, it would be a fault code. So we convert that top 8-bit number back to decimal. It is 2, and I looked this up in the MOVITRAC LTP-B manual, and 2 simply means the VFD is not enabled. And that makes sense because we disabled the VFD to bring it to a stop. All right, let's check the other bits. We'll start with bit 0, controller inhibit. There's a 0 there. That means yes, it is controller inhibited. Bit 1 is a 1. That's yes for ready, so the VFD is ready to run. And bit 2 indicates whether it's listening to POs, and there's a 1 there, which means yes. No big surprise since we're operating in field bus mode. So that's PI1 when the VFD is stopped. Now let's look at it when it's running, 05C7. Let's fill in the bits. I converted 05C7 to binary using the Windows calculator. And here's what it translates to when you turn it into bits. Again, we'll look at bit 5, the fault bit. It is still 0, so that means the top 8 bits make up a status code. We convert those 8 bits to decimal, and that is 5. I looked up 5 in the MOVITRAC LTP-B manual, and it means that it's running in speed control mode. No big surprise again, that's exactly what we were doing. All right, let's look at the bottom 3 bits. Bit 0 is a 1, that's controller inhibit, so we are not in controller inhibit, and that makes sense. We wouldn't be running if we were controller inhibited. Bit 1 is a 1, that means we're ready. No big surprise there either, and bit 2 also is a 1. It means yes, we are listening to POs. So that is our process input word 1, the status word. By the way, you may be curious about those 2 1 bits above the fault bit. They're in black. That's because that's not part of the normal 3PD status words, so we just ignore those. But you can look those up in the manual, and they actually do have a significance, but it is unique to the MOVITRAC LTP-B. It is not found in some other SCW Eurodrive products that use 3PD, which is why I didn't talk about those bits. They're not really important for what we're doing. All right, let's move on. We're going to take a look at PI2, the running speed. This is the feedback from the VFD telling us how fast it's turning. It pretty much should match the value we send in PO2. It may be slightly different, but it should be close, at least once the VFD is at a steady state. Of course, it will change as the VFD accelerates and decelerates, but I took this reading when we were just running smoothly. So here's how we interpret it. We have to take our parameter 1-01 value to know the motor's maximum speed, which in my case is 1800 RPM. And then we take that hexadecimal value coming back in PI2. We convert it to decimal, which is 13,648. It is a positive number, so that tells us we're turning clockwise. We divide that by 16,384, which is 0.833, 83.3%. We multiply that by the P1-01 value, the maximum speed the motor is supposed to turn. So we multiply that by 1800 RPM, and we get 1499 RPM clockwise. And that makes perfect sense because we were trying to run at 1500 RPM when we got this speed. So we're pretty close. Pi3 is the amount of current the motor is drawing, and again, this is going to change too as the motor accelerates and decelerates, but in my case, it was a steady state value. So I captured that, and we need to turn it into amperes. Now we need to look at our P1-08 value in the VFD, which is set to 1.8 amps. That's the motor's nominal current rating. And then we take our Pi3 value, 00B5, we convert it to decimal. It is 181. We divide it by 1,000, which gives us 0.181. That's 18.1%. We multiply 0.181 times the nominal current, 1.8 amps, and we get 0.326 amps. So that is the amount of current the motor was drawing at the time I took this Pi3 reading. So you can see we get a lot of information back in those 3 PIs. They tell us pretty thoroughly what the VFD is doing, and our PLC program can interpret those if it needs to see what's going on. All right, well, let's move on now. We're going to explore terminal control mode when you're running in field bus control. As I've said before, we have limited terminal control mode when we're operating in field bus mode. And just to remind you, I did select variant 1 as my choice, so this is the assignment of the different digital inputs and analog inputs. We've used this variant before in pure terminal control mode, but it is going to be modified slightly by the fact we're running in field bus mode. Let's just review what the inputs do. Digital input 1 is the stop run input. It's kind of the enable of the VFD. Of course, we've turned it on so our VFD can operate in field bus mode. If you turn it off, it will prevent the VFD from running. Digital input 2 is a direction control input, so it controls forward and reverse. We can actually override whatever the field bus is telling it to do and change direction. I'll demonstrate that in just a minute. Digital input 3 selects between the selected speed reference and 2 presets. Now in the past, this has been a potentiometer when you had this switch turned off, and it would go to presets when you turned it on. But when we're in field bus mode, it's going to ignore the potentiometer. It's going to use the field bus for the speed. So when this switch is off, we should have the field bus speed, whatever that is. But if we switch it on, we should get either preset 1 or 2. Analog input 1, which is still connected to a potentiometer on my VFD, is actually going to be ignored because the selected speed reference is no longer the potentiometer, it's the field bus, so this input is kind of a pointless one. And then analog input 2, digital input 5 selects between preset 1 and 2. Since I have a potentiometer there, I'm going to be using it like a switch by turning it all the way down or all the way up. So I'm going to try out all these functions in just a second to see if they work as we expect. And I'll just remind you what my 2 presets currently are in my VFD. Preset 1 is 1500 RPM clockwise, and preset 2 is 500 RPM counterclockwise. So let's go back to the Ethernet Master Simulator. I'm going to fire up the speed, and then I'm going to go to my VFD and flip some switches and see if it behaves as we expect. All right, well, we need to get our motor turning first of all. So we're back in the Ethernet Master Simulator. What we're going to do is pick negative 750 RPM as our running speed. We'll change PO1 to 6 for running. Then we're going to change PO2 to E555, which will give us 750 RPM counterclockwise. We'll just keep the ramp here at 5 seconds. And we'll go ahead and start our motor by clicking Update PO. So that will get us rolling. And now we're going to switch over to the terminal control, and we're going to start seeing what we can do with it. First thing we're going to do is try the forward reverse switch. So I'm going to turn DI2 on, and that's going to reverse direction. You can see it overrides the field bus direction. We'll go back now. So that works. Now we're going to try the presets. Digital input 3 controls them. It's off right now, which selects the field bus, but when I turn it on, it will switch to presets. Digital input 5 selects between them. We've selected the first one. So I'm going to engage it here. And you can see we're going to go to 1500 RPM clockwise. And now I'm going to turn the potentiometer all the way up to select the second preset, which should be 500 RPM counterclockwise. And it is. Now let's go back to field bus control by turning digital input 3 off. We're back to 750 RPM counterclockwise. And the last thing we'll do is we'll just turn digital input 1 off, which disables the drive, and we'll re-enable it. So everything seems to work as expected. Now let's do the last thing. Let's create a field bus fault by disconnecting the network cable. So we'll remove it there. And after 1 second delay, you can see it goes into shutdown as it's programmed to do. Notice it doesn't fault. It's not supposed to. It's just supposed to ramp down and stop. So it looks like everything is working as expected. All right, one final thing I want to mention just very briefly before we wrap up this very long session, and I commend you for hanging in there. We're not going to cover field bus communications using the gateway. As I mentioned in our last session, that's already been done in the MOVITRAC LTP-B Plus video, and I point you to that, but I did want to just mention one thing to clarify how the field bus gateway works. If you are using a field bus gateway, it uses what is called 24 PD control. And you can guess what that means. It means a lot of process data words. Now, as you recall, if you're using the gateway to connect your PLC to your VFDs, you have a maximum of 8 VFDs on a local S bus, which is attached to the gateway. And then the gateway has your main field bus on the other side. You may wonder how this works as far as process output words. Well, in a nutshell, the gateway assigns 3 POs and 3 PIs to each VFD on the S-Bus network. Now, it is really smart to set your addresses sequentially in ascending order. And that's because the gateway assigns the process output words based on the address order. So if you make everything in order, it just makes your life simpler. You don't have to do it, but it's really smart. So what will happen is the PLC will send 24 POs to the gateway, and the gateway will divide those up into units of 3, and it will send 3 to VFD1, 3 to VFD2, and on down the chain to 8. The VFDs will send back their PIs. The gateway will assemble them into a big block of 24 PIs, and it will send that back to the PLC. So it's kind of like this. The lowest address on the gateway, which in this case is 1, will get process output words 1, 2, and 3, process input words 1, 2, and 3. The next VFD will have process output words 4, 5, and 6, and PIs 4, 5, and 6, and on down the chain till you get to the last VFD, which has the highest number address. It will have PO 22, 23, 24, and PI 22, 23, 24. So you can see working with the gateway is kind of like working with one big chunk of POs and PIs, but this is how it divides them up. And by the way, this is the reason you're limited to only 8 VFDs on a gateway, because you can only send 24 POs and PIs. This is how it works. So that's just a little heads up if you're using a gateway. And with that, I'm going to end session 12. Congratulations for hanging in there. You did a great job. Our next session, which is our last and the end of the course, is a nice, short, simple session. We're going to look at controlling non-asynchronous motors on our VFD. We're going to control a permanent magnet synchronous motor, also known as a servo motor, and then we're going to wrap up the course. So come back for the last session, and for the wrap up, see you next time.